All right, hey, welcome back. I hope you got those, coordinate points things taken care of because we're going to use those a lot today. But before we jump into all of that graphing stuff, let's talk about two variable equations, most commonly called functions. So let's go ahead and head to the board so we can see some examples. So a function often has a name, and usually it's some function of x. So f of x just means function of x. Sometimes we write it as a y value. In fact, a lot of times you'll see it written as y. So just know that y is a function of x. So the way a function works is, so I like to describe this to my students as kind of a car. So if you have a car, there's stuff that you put in the car to make the car work. So you got the gas, you put the gas into the car, and the car moves, right? So you input something and it outputs something else. In this case, you put in the gas and the car puts in the miles, so to say, as it drives down the road. Functions work in a very similar way. So we have a function and we have some numbers. We have numbers. We're going to call those x. So x could be certain numbers. And we put those numbers into the function. So when we put those into the function gives us our y values, or also known as our f of x values. And that is going to be a bunch of other numbers. Now, those numbers don't have to be the same, but they can be. So basically, x gets put into f of something, and then that something becomes your y value, pretty much. So the function is just the operation that's happening in the middle. It's relating these two variables in a specific way. And there are specific kinds of functions that do specific things. One of the ones we talked about in the previous lesson was absolute value. So if I were to describe the function of absolute value, that would mean that f of x is equal to the absolute value of x, or that y is equal to the absolute value of x. So x could be any number I could think of. So I could put in -3, -2, -1, 0, 1, 2, 3, so on and so forth, right? Meanwhile, the y value is dependent upon the x value. So that's what makes x the input, is that you need to know what x is in order to know what y is. So y would be the output, the gas and the miles, so to speak. So absolute value of -3 would be +3, -2 would be +2, 1, 0, 1, 2, 3. And this is essentially how a function works. You just plug something in, you get the other thing. Now, this is useful when we're trying to describe how two numbers are related to each other. So, for instance, let's say that my age is T, because I'm Thomas. So let's say my age is T. I happen to be 5 years older than my sister. So let's say that my sister is S plus 5. So however old my sister is, if you add 5, you get my age. Now, there's some algebra you can do to play around with that so that you could just, know my age and then you get my sister's age. But the point is, this is a function that puts my sister's age into the equation and tells me my age. Now, I don't necessarily need this in everyday life. It's just an easy example to go with. Something that might be a little bit more important might be, so let's say the number of miles you can go in your car based on how much gas you have left. So this is a function, miles of gas. So you can go, so let's say your car goes 40 miles per gallon, right? Okay, so 40 times G, that tells you about how far you can go, to get your car to where it needs to be. So when you know what G is, you know what M is. So if, say, for instance, G is 3, then you would know that M of 3 would be 40 times 3, which is 120. So you'd be able to go 120 miles before your car runs out of gas, at least theoretically. So in that situation, that is useful information that you got because two values were related by a function. Very, very useful. It also means that we can tie variables together on the Cartesian coordinate plane. So for instance, let's say that the gas is the x values and that the miles are the y values. So at a g value of 1, you have 40 miles for the car, right? Okay, cool. If you have 0, you have 0, so I'll just put a big dot right there. At 2, you have 80, so on and so forth, right? So neat thing about this is that you can actually draw a straight line through this. So this is what we call a linear relationship, or a relationship that draws a straight line. We'll dig more into that here in a little bit, but now we know that this is a kind of relationship. And so if we know certain things about this kind of relationship, we know how variables like this should interact with each other, which means that we don't even necessarily need to know what the variable is to know how it works, which is very useful information in a lot of situations. Now let's jump, oh, I got a little thing there. Yeah, okay, now let's jump back to the presentation. So we talked a little bit about what a function is. A function is basically a two-variable equation. And now, so drawing equations, okay, so we already kind of did that, but let's do another one that looks a little bit different to show you what it looks like in a different scenario. So let's go back to the board. So we did a linear equation. Now let's do one that's not quite so linear. So let's say that y equals x squared plus 1. Okay, so we've got an x-axis that is using x, and y-axis that is using y instead of m and g. So that means that whatever x is will tell us what y is. So let's say we plug in -3. Okay, so -3 squared plus 1. So -3 times -3, that's 9. 9 plus 1 is 10. So we know that the coordinate point -3, 10 is on our graph. Excellent. So now if we do -2, 2 times 2 is 4. 4 plus 1 is 5. So that's another point that we can put on there. We can put the coordinate point -2, 5. And if this were a linear graph, we'd be done. But it's not quite. So here's, sorry, we're doing the negatives. I don't know why I put that over there. So -3, -2. So we know that -3 is way up here at 10. So let's extend this a little bit and say that's 10. And then -2 is way down here. Let's say that's about 5. Okay. So then we plug in -1. Okay. So 1 times 1 is 1. 1 plus 1 is 2. So then we have -1 at 2. And this is where something interesting happens. So now if we try to connect two of our dots, oh, hold on, I need to make the line work. There we go. So now if I try to connect two of my dots, wait a second, I'm missing a point. I can't hit one. So this is not a linear relationship because it can't draw a straight line through all of my points. So this function is not linear. That's important information. We don't necessarily need it right this second, but it's good to know. So now let's plug in 0. So 0 times 0 is 0. 0 plus 1 is 1. Okay, so there's 1 right there. Okay, and I'll draw that line through it like that. Okay, so when we plug in +1, 1 times 1 is 1, plus 1 is 2. So we're back up to 2. Then we go 2 times 2 is 4. 4 plus 1 is 5. So now here at 2, we are back up to 5. And then we plug in 3. 3 times 3 is 9. Plus 1 is 10. So we're back up to 10 again. All the way over here. So now, if I connect these dots, now we see that this particular function is very different from y equals, x. It's y equals x squared. This is a quadratic equation. This one is a curve. So we're going to talk about tricks and things you can do to draw a linear equation easier. But if you have no idea what your function looks like, you just don't have a darndest clue in the world, just start picking random x values and plotting out some points. So each of these refers to each of the points that we drew on this chart. So if you can write the dots, then all you got to do is connect them, right? Just a nice little game of connect the dots. And we got a nice little function here. Now, this doesn't always make it easy to graph it, but it does give us a fallback plan if we aren't sure what to do. So when in doubt, just pick some x values, plug them into the equation, get some y values, and plot your points. Okay, and that is essentially how you draw equations. You just plug in the x values and then look for your y values. So now we're going to talk about linear equations. Okay, so linear equations are written in the form of y equals mx plus b. If you've been in Algebra 1, you've probably heard that before. If you haven't heard that before, don't worry, we're going to go over it. So linear equations are... Sorry, I'm getting the... So with linear equations, the way that we draw them is we break them down into parts. So as we did before, you can, of course, just plug in y's and get x's. But when it comes to linear equations, they are actually set up in a way that makes it easier for us to figure out what's going on. So it's y equals mx plus b. So m is what we refer to as our slope. So the slope is basically how quickly it gets taller. So how fast it goes up relative to how fast it goes forward. So change in y over change in x. So for instance, if we were to have two equations, so let's say we're right here. So let's say we have one equation that goes like this and another equation that goes like this. So one of these guys, as we move to the right, is moving up. So there is this change in x that tells us how far it moves forward, and there is a change in y that tells us how far it moves up. Now on this equation, there's also a slope with its own change in x and its own change in y. But you'll notice that not only is the ratio of x to y here very different on this first one, we don't actually need that much x in order to go up very quickly. And on the second one, we need a lot of x before we can go down at all. But you'll also notice that the second equation is going down as it goes. So, you know, it kind of stair steps this way, so that as you go right, you have to go down. So that would make the slope negative. And you can have negative slope. That's perfectly fine. It just means as you move left to right that your equation is moving down. We'll look at some examples of both. But that is what slope is meant to do. It's meant to look at how quickly am I moving up relative to how quickly I'm moving forward. And this second bit here, the b, is what we call our y-intercept. Hold on a sec. Is our y-intercept. So the y-intercept is where we cross... So where we cross the y-axis. So drawing some more functions. This time let's use green. And let's get fancy, use orange. So these guys have different slopes, similar to before. However, they also have different y-intercept values. So the y-intercept value is just where we cross the y-axis. The y-axis is the one going up and down. So whatever y value we have here where we cross the y-axis, that's going to be our value for b. It is also the place where x equals 0. So if you need to solve for it using algebra, you can just make x 0, and that'll work just fine. So in terms of graphing this, so let's graph this real quick. So, you know, assuming that we understand how slope and y-intercept work, actually, I'll leave those up while we do this first one. So let us say that we have y equals, let's say 2/3 x plus 2. Okay. So we make ourselves a neat little equation here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so we'll say that our first point, we'll mark it with an A. So our first point, actually, we'll mark it in blue. So our first point starts off at 2. So we start off at the origin, always starting here at the origin, right there. That's where we start. we're going to move up 2, and we're going to put a point right there. And we will have this point because our y-intercept is 2, so the point specifically is 0, 2. So y-intercepts x is always 0, so x is 0. We know that much. And we know that the y value, in this case, will be 2 because this number right here is 2. So we got a point right there. Neat. So now we go over to the slope, and now we got to recognize, okay, which part does what? So the top is our change in y. That tells us how far to go up. And the bottom is our change in x. That tells us how far to go right. So according to this equation, I should go 2 up and 3 to the right. So 1, 2, 3. And I should have my point right about there. So if I have 2 points, then all I need to do to draw a line between them is to extend my line like this. So now I've got a line that's going through both of my points. And bam, now we have graphed this equation right here. We've got it all marked out right here on the chart. And that wasn't so bad. So this is how graphing a linear equation works. You use your y-intercept and your slope in order to help you kind of get things moving along. So let's do one more example. This time we'll do an example that has negative numbers, and we'll see how that works out for us. So, delete all that. Make sure the board's nice and clean. Okay. So now let's say we have y equals -1, let's say 1/4 x minus 2. Okay. So again, it's going to start with the blue, and it does take the negative into account. So we're not just going up 2, we're going down 2. So let's say we go down 2. So let's say this is down 2. And according to this guy right here, I should be going 1. So normally I would go up, but since it's negative in this case, I'll go down 1. And I'll still go 4 to the right. Whenever you have a negative slope, it's easiest to just remember that you're going down instead of up. So if I go 1 down, so 1 down and 1, 2, 3, 4 to the right. So those are my points. And now if I go ahead and draw my line, then this line is going to be a lot flatter than the other one. And it'll also go down. So let's see, going through our points. Yeah, so this one is much flatter than our previous one because our slope is, it's closer to 0. It is a fraction. And it's going down because it's negative. And that is the easy way to graph linear equations. Sometimes you'll get a linear equation in other forms. So one you might see a lot is ax plus by equals c. Don't worry too much about all of this. We've already talked a little bit about how to use algebra to move terms over. So my advice would be if you have something like this, just turn it into y equals and then go from there. You can still plug in x values to figure out what y is. You can still do it that way. That's plenty fine. This is called standard form, which I just kind of find funny because usually, or at least by my standards, I don't see standard form very often. So just be aware, if you do get an equation that way, it is still perfectly fine to plug in an x of your choice and figure out what y is and draw your points. Or you can use some algebra to get it into slope-intercept form, which is what this is. Y equals mx plus b is what we call slope-intercept form, which is the form that I prefer and the form that I'm used to seeing more often. So with that in mind, we are now going to go ahead and clear the board. And then we're going to flip back over to the notes to see what we got next. Okay, so linear equations, that's how we graph them. So now, making a line with 2 points. Okay, so we're not talking about drawing here because as I showed you, if you're able to just draw the straight line between the 2 points, that's not that hard. All you need is a pencil and a straight edge to make it happen. However, the formulas for doing this, when you have points to work with, can be a little bit tricky. So we are going to go ahead and switch back over, and we're going to talk about how that works. So slope, so earlier I said slope, I used a brush. So earlier I said slope is equal to change in y over change in x. So what does that look like? How do you get that? Well, assuming that we don't have, a graph to work off of, change in y is just the difference between two y values. So, basically how far you go up or down between 2 points. And the change in x is the same thing, but for x. So real quick, let's take 2 points and get the slope of a line between them. So let's say we have 0, 0, and let's say we have 1, 4. Now, in case you are worried that you'll mix these up and you're not sure which one should be which, keep in mind that x1 should always be less than x2. So whichever of these points has the higher x value, that one is x2. So in this case, this guy would be x2 because 1 is definitely bigger than 0. Which means this would be y2, which means this would be this would be x1, sorry, my bad. This would be x1, and this would be y1. So, rise over run is how a lot of people remember it. I remember it that way in my head because the y value is how far you're going up. So this would be your rise, and x is how far you move forward. So that I would consider to be your run. So I always remember it as rise over run. So rise, so y2 is 4 minus y1 is 0, and x2 is 1 minus x1 is 0. So that's going to give us 4 over 1. So that means that our slope is going to be 4 because this is the formula for slope. So we have a slope of 4. Awesome. So that would be how we'd find a slope. So now we need to do a y-intercept, b. So our b value is going to be equal to y minus m times x. And these values of y and x, they can be anything as long as we have a point to work off of. So for instance, over here, the point 1, 4, we can make this work. So according to our calculations thus far, we don't know what b is. We know that y is 4 because in this point, the y value is 4, minus m, which also happens to be 4, multiplied by our x value. Our x value is 1 for this point. I want to stress that I am using this point. When it comes to the y-intercept, you don't have to use this point. You could use the other point. Any point on the line works. I'm just using the one with numbers because the numbers make it a little easier to track what's going on. So here, so we'd say b is equal to 4 minus, and then 4 times 1 would, of course, be 4. So 4 minus 4 is 0, which means that our b value would be 0. So if I asked you, what is the equation of a line that runs through these points, you would say, well, I know that the slope is 4, and I know that the y-intercept is 0, so y should equal 4x plus 0, or, because adding 0 is kind of like, it's a thing that's nice, but you don't really have to do it. We could say y equals 4x, and that would also be a correct answer. Both of these answers would be correct. It's just that one of them doesn't have the plus 0, because a lot of people tend not to write that plus 0. And so now that we have, the equation of the line, we can go ahead and graph that like we were talking about before using slope and y-intercept, which, that's nice. It's nice for us to be able to go back and forth as we need. So with that out of the way, let's go ahead and clear the board. Okay, and now let's cut back to the notes. All right, so over here, we just went over it. So you start by getting the slope. Once you have the slope, you can substitute in x and y from any coordinate pair. So any point that you know is on the line, you can use those x and y values. And then once you have the slope and y-intercept, you have the equation. And now that you have the equation, you can graph it however you want. So next up, let's move on to parallel and perpendicular. Okay, so parallel and perpendicular, we're going to talk about those as a concept first. And then we'll talk about how those work with numbers and trying to make those into linear equations. So parallel, so hold on, let me move over. So parallel, so if two lines are parallel, so let's say we have y1 and y2, and this sign right here means parallel, so it means parallel. So if y1 and y2 are parallel, what that means is that if we draw these, so here, I'll make, so I'll make y1 in red. So let's say we have y1's like this, and then let's say we switch over for y2, so y2 is in blue. So y2 is exactly the same line. It's just moved down a little bit. So these two lines that we have right here, they are never going to meet. One is literally just the other moved up. So it doesn't matter how far I move left or right. Y1, aka the red one, is always going to be a set distance away from Y2. So there's no way these two are ever going to touch. If they don't touch, they are parallel. Now, as a byproduct of them being parallel, because they are parallel, that means that their slopes have to work in the exact same way. Because if they didn't work in the exact same way, then these two lines would be touching. So if y1 is a function and it has its own slope, so that slope would be n1. Y2 is another function whose slope is going to be the same as the slope of the original. So if two lines are considered to be parallel, then you could just treat their slopes as the same. So let's say I have y equals 3x minus 4. And I want to, make up a line that is parallel. So I could say y equals 3x because now the slopes are the same. And now I can add or subtract pretty much anything I want as long as it's not -4. Because if I write -4, it'd be the same line and the line can't be parallel to itself. That's not how that works. So here I'll just write +4. And now if this one can be called y2, that one can be called y1. So now y1 and y2 are, as a matter of fact, parallel to each other. Their slopes are the same. And of course, if I wanted to say they ran through a certain point, then I could say, y2 equals 3x plus b, and then whatever point it is, plug in x, plug in y, and then I can get my b values. So that's how parallel works. So parallel is pretty straightforward. So now we're going to talk about a little something called perpendicular. Oh my goodness, I did not want those lines, please. There we go. All right, so now let's talk about perpendiculars. Because perpendicular is, it's a bit strange. So perpendicular, so if, no, I want the brush, please. So if two lines are perpendicular, so if we got y1 and we got y2, so if two lines are perpendicular, then that means that their slopes are what we call negative reciprocals. So, over here, we got m1, and if we were to flip it, so this is m1 over 1. So if we were to flip it and make it negative, so negative 1 over m1, that would give us m2. Almost forgot the negative there. The negative is very important. Don't forget your negative. And so what I mean by perpendicular, so perpendicular means that these two sets of lines have a perfect 90-degree angle. So let's say, I'm making a line, and this line, it's minding its own business. It's going the way it goes, got the solid color there. Okay, so this line is working just like that. That's just how it is. That's just what it does. So no, I wanted that to be blue. Thank you very much. And now let's say the next one we want to make red. Okay, so we make this line in a very specific way. So it has to have a specific slope. There we go. That's much better. So it has to have this slope specifically because this slope creates a 90-degree angle between our two lines. So whenever that happens, essentially what we're doing is we are doing -1 divided by the other slope in order to get this. So if this slope over here is m1, then the slope of this guy over here is -1 over m1. This is a little bit harder to see with normal letters. So what I'm going to do is we're going to go ahead and have an example. So let's say y1 equals 3x plus 2, and we need to make y2 perpendicular to it. So according to my rules, I need to do -1 over the thing. So, or I need to do the negative reciprocal. Reciprocal means I need to flip it upside down. So 3 is the same as 3 over 1, so its reciprocal would be 1/3. But we're doing parallel, so just the reciprocal isn't enough. I need to make sure it's a negative reciprocal, so it's -1/3 times x. Now, the cool thing about perpendicular that parallel doesn't really get is perpendicular doesn't care what you're adding to the equation. They are still perpendicular because perpendicular functions meet by definition. So I could slap +2 on here and it wouldn't be a big deal, even though with the parallel one, I would have to add something different. With perpendicular, just by, the nature of the slopes being different, that means that they're automatically going to collide somewhere. So in this case, they collide right here. So this would be the point where the two lines meet. You're not going to be asked to find that in this unit, but maybe later, whenever we're working on different kinds of functions, this is something that you might do. So, so just remember, if you are looking at parallel lines, that means that the lines have the same slope. Whereas if you're looking at perpendicular lines, it means you need to flip the fraction upside down and make it negative to go from one to the other. And so that just about covers the parallel and perpendicular stuff. So we won't be needing to go over that again too much. It might it'll pop up a little bit in the future. But for right now, we've got everything we need from it. Okay, so let's go back to our thing. Okay, so that's parallel and perpendicular. And that is it for the linear equation stuff. Again, this is the the word problem activity that I'm going to be going over in the synchronous session. So hope to see you there. We can talk about that. But for now, that's everything. So hope you have a fabulous day, and I'll see you next time. Bye-bye.